Okay, now it's Eva, we're just doing a quick audio test.
Hello, everyone. My name is Eva Keitel, and I'm excited to be hosting today's webinar. This webinar is entitled, How is AI Changing the Project Management Landscape? This presentation examines how AI is now being used to proactively guide and validate the entire project planning process, capturing historical project performance and leveraging data to validate new plans is a huge step forward for the industry. We are pleased to note that this webinar is sponsored by InEight, a dedicated CII member. This presentation will likely result in questions, so as they come to mind, please type them into the panel box on your screen. Questions will be answered at the end of the presentation. Our presenter is Dan Patterson, Chief Design Officer at InEight. His lifelong passion is to better the project management industry. In the past 20 years, he has founded 3 project management software companies and developed tools that many of you use today, including risk analysis, schedule diagnostics, and AI-driven planning. His goal at InEight is to convert what is a vision for next-generation predictive planning into a reality. Without further ado, I would like to hand it over to Dan to begin.
Well, Eva, thank you very much for the warm introduction. And for everyone joining this morning, good morning. I'm very excited to spend the next hour with you all, sharing my thoughts and in many ways my passion with regards to how I believe artificial intelligence and machine learning is truly improving the science of project management, and more specifically the science of project planning. So what I'd like to do in terms of the agenda is, first of all, just really set the scene with regards to, well, why do we even have a need for improving planning and scheduling? Surely after so many decades of software evolution and proven tools and techniques, why do we even need the likes of artificial intelligence? And then from there, I'd like to lead into really a primer with regards to, what exactly is artificial intelligence? There's a lot of noise and speak today around AI and things like neural networks, machine learning, so on and so forth. And I think, some of it, while I think some of the terminology is hype, but the reality is there is something very, very valuable in this this technique that is rapidly developing and becoming much more mainstream in software. I'd like to tie that back, obviously, then to planning and share with you how artificial intelligence and machine learning is being used to push planning software really into what I believe to be the next generation of software tools. And then as a wrap up, a little bit of food for thought, I guess, with regards to less around AI and machine learning and more to do with the convergence of scheduling and cost estimating and risk analysis. So hold that thought, but we'll look back on that at the end. So let's start off with the state of capital expenditure planning today. So the basic gist of CapEx planning and scheduling is very simple. What we're trying to do is we're trying to forecast as accurately as possible how long and how much investment, how much capital investment a project, a temporary endeavor will take. And when you look at it at face value, we think, well, that's actually very simple. Why is it so complicated? Surely we're just trying to establish timelines. Well, the reality is to accurately forecast those timelines actually involves looking back over historical information and really trying to draw analogies as to, well, historically, how long did certain types of work take? And then on top of that, sequencing those work elements. So the durations and the sequence of work come together to form what we call a critical path schedule, or a CPM schedule. And many of you today, I know, will be using standard CPM or scheduling tools to run that calculation. One thing I found, I guess, interesting, fascinating, arguably a little bit disturbing, is the fact that CPM scheduling tools today, they focus on work, and they don't really focus on scope. What I mean by that is, when you start off with a blank digital sheet of paper in a traditional scheduling tool, the first thing you do is you create a WBS structure, your framework, and then against that framework, you start defining work. Well, in my mind, that's a little bit ridiculous, because how can you define work without, first of all, understanding and defining what it is you're building? In other words, the scope. So it's always been my thinking and belief that really we should start with the deliverables of the project. Let's start with the overarching scope of the project. Let's break that out into key deliverables, and then against each of those key deliverables, let's figure out how much work needs to be expended in order to achieve those deliverables. Because at the end of the day, an owner organization in many ways cares less about the work that's being expended, but really they ultimately care about the deliverable, which is the asset that's being delivered through the project. And so I think in some ways, from a software vendor perspective, we've fallen short as an industry with regards to providing tools that truly link scope and work together. And I think as a result of that, in 2019, it's the exception for a major CapEx project to complete on time and to budget, rather than that being the norm. And again, it's my belief that it's not actually execution that is the root cause of that problem. It's the fact that the plan that we put together upfront and initially defined and used to track throughout the project lifecycle, that if that plan is overly aggressive and unrealistic, then irrespective of how well we execute the project, we're always going to perceive our project to be late and over budget, because we're comparing it against something that is unachievable. So, really that was a long-winded way of saying, if you look at project management as a whole, I think we're actually doing a fairly good job in the project execution phase with regards to things like performance tracking. I think it's the upfront planning that needs additional work and additional attention. And again, with regards to planning, what we're trying to do is forecast the future by taking into account historical performance and historical experience. And to date, that's been very difficult to achieve with computers. And the reason being, computers, in absence of artificial intelligence, are very good at dealing with structured data. In the most fundamental sense, computers can literally do simple mathematics. That's it. They're not very good at dealing with unstructured or more sort of soft entities. And so historical project performance data is rarely in such a structured format, such that a computer can make much sense of it. Now, with the advent of artificial intelligence, computers are actually now starting to be able to mine what we call non-structured information and knowledge in a much more meaningful manner. They're able to draw inference and make suggestions in absence of having data stored in a highly structured format, such as in a database. Now, on the left-hand side here, there's several definitions as to exactly what artificial intelligence is. I've summarized those on the right-hand side, and the way I think of artificial intelligence is the ability for a computer, through understanding of context, to learn from past historical data. So first of all, I think it's important to understand here, computers need to understand context. If I'm a planner and I'm trying to put together a cost estimate and a schedule forecast for a particular type of project, the computer needs to understand that context such that when it guides me through that planning process and it makes suggestions, it's coming up with relevant information. And then tied to that, the second part of that statement, intelligently putting forward suggestions as to future state in a manner that is akin to human expertise. And I think, again, what's important to note here is I don't believe that an artificial intelligence planning system should hold the responsibility for generating a cost and schedule forecast. What I believe is that an AI engine or AI planning solution should augment or assist the planner, the cost estimator, the scheduler. I see it as almost like a sort of a personal planning assistant, rather than actually replacing the expertise of the planner. So that leads us into really a subdomain of artificial intelligence called machine learning. So again, in very simple terms, machine learning is the ability for a computer to automatically adjust its behavior or its algorithm or its thinking based on its environment. And again, from a planning perspective, I think this is very important, because if we can get a planning computer software package to the point where it's supposedly smart enough to make suggestions, that's great. That's a massive leap forward from what we have today. But if those suggestions are arguably erroneous or out of context, the computer needs to be humble enough that it can actually self-adjust and readjust its thinking such that over time, those suggestions become more and more accurate. Again, another way I think about AI is to think that traditional planning software really involves me, the planner, sitting in front of a computer, and I'm telling the computer information. I'm telling it activity descriptions. I'm telling it the linkage between activities. I'm telling it durations. The computer just does a calculation. It's not actually giving me any form of feedback with regards to, well, is that a realistic estimate or forecast that I'm putting together? So in my mind, artificial intelligence is really now, it's the first time where the interaction between me, the human, and the computer is now bidirectional. And while we're in the very early stages of developing AI-powered planning software, I think we are at the gates of something very, very exciting and interesting in the coming years. So taking that theory and applying it a little bit back to I guess, more to reality. So how does machine learning actually help us better plan? Well, the concept is very simple. So again, the planner is still ultimately responsible for building the cost estimate and the schedule forecast. And just as if I was sitting down with a piece of paper, what I'm doing is I'm leveraging historical information in order to put my future forecast together. The difference, though, with AI is that instead of me having to rely on my experience or walk down the corridor and talk to discipline leads or domain experts, the computer, by storing that expertise from multiple contributors and multiple prior projects, it's the computer then that is actually making those suggestions and those critiques. The planner then still gets to either adopt or reject those suggestions. So, prior to this improvement in planning, I think CPM scheduling has very much been a silo exercise. It's been down to the expert planner. The organization and the project relies on their expertise. Well, that's a very high risk endeavor. We're assuming the planner has sufficient historical experience, and we're also assuming that that planner will remain within our organization for a long period of time. AI actually diminishes that risk because, firstly, you're getting suggestions again from multiple contributors through that digital information, and secondly, from an organization perspective, that expertise, if an organization can capture that experience and that expertise and then start to reuse it through the suggestions that the AI engine can make, then that actually lessens the dependence of an organization on, for example, key planners, schedulers, or cost estimators. So with regards to how exactly does the computer make suggestions when the AI engine goes off and mines information, there is a technique that uses something called a neural network or a neural net or neural nets. And just to give you a taster as to how a neural network works, again, in the context of planning and scheduling, let's take an example where we are asking the computer to validate a duration for an activity that we're developing or planning. Now, if I were to say to you, okay, what's the best way of going into a historical schedule and looking for an analogous activity, you'd probably say, well, I'm just going to go and do a description match. Well, that's all very well, but in reality, the chance of two different projects defining the same scope or same type of work using the exact same description is actually very, very low. So the way a neural network works is, instead of using a single attribute to do that match, it actually uses an array or multiple attributes. So in our simple example here, we have a description, we have the phase of the project, and we're also looking into whether the logic coming in and out of an activity is the same or not. So those three attributes actually carry an importance factor or a weighting. So in our example here, we're saying the description has a weighting of 3. If the activity is in a similar phase with regards to timing in the project, it's a 4. And if the logic is similar, it's a 3. So interestingly there, the description actually carries a lesser importance than, for example, where the activity falls in the project lifecycle. So with that, if we take an example where on the left-hand side here, the description indeed matches. So the computer's going off, it's trying to do a search and a return or a match, and it's saying, okay, I found an activity where the description matches, but the activity in question falls in a very different phase, and the logic going in and out of that activity is very different. Because the description carries a low weighting, the net result score is actually relatively low. In this example, it's a 3. Conversely, if we find an activity irrespective of the description matching, so the description in this case doesn't match, but the activity happens to be in a very similar phase of the project lifecycle and the logic is similar or the same, then that activity actually generates a much, much higher score. The reality is the computer has probably found the correct activity despite the fact that the descriptions don't match. Okay, so that's a simple example of how a neural network is used to do pattern matching with regards to project planning. And I think, you know, the opportunity here is so high because when we think about a project schedule, there are so many attributes that drive understanding of context that there's a big opportunity to apply all of these attributes such that these neural networks and these what we call an inference engine, these engines can actually become very, very smart and very, very accurate. So that's a little bit of background information with regards to AI and neural nets and how they work behind the scenes. The slide that we're looking at here really walks us through the workflow process. So on the left-hand side, we have really the responsibility of what we call the knowledge administrator. This is the person that is responsible for capturing the information that gets stored in the planning software. You know, and this can be historical schedules, cost estimates, risks, so on and so forth. And then the second step is to classify that knowledge, and that classification actually helps then with the identification of those attributes as we saw in the prior slide. And then thirdly, we have a machine learning element, and I'll talk a little bit in a few minutes as to the importance of that machine learning. So once we've captured and classified and trained the AI engine, as you can see on the left-hand side, then we roll over to the actual use case where the planner is then able to, in a more intelligent and accurate manner, create their plan and their forecast. And again, irrespective of AI and machine learning, what I'd also like to suggest in this webinar is that instead of considering a project plan as a single entity, you know, I think, again, you know, because of the nature of scheduling tools today, when we think about a project plan, we think about a CPM schedule, and that's it. Well, I'm not sure that a CPM schedule necessarily is relevant or fits all phases of a project lifecycle. You know, in the very early concept phase of a project, where you may not even have enough definition to put a true CPM schedule together, then, you know, at best, a CPM schedule is overkill. What I think is probably more relevant is to have more of a top-down forecast based on high-level timelines. That then can be the starting point for your CPM schedule. And then the third step, and I think this is certainly a very new area within planning, is that around field execution planning. Field execution planning sounds like a bit of an oxymoron. Is it planning or is it execution? Well, it's actually planning during the execution phase, because during execution, what we're doing is we're trying to execute very short-term segments of work. So typically, a field execution plan wouldn't look any further than, say, 2 weeks out. And so that 2-week look-ahead plan is a very different beast to perhaps my 3 or 4 year long-term look-ahead using a CPM schedule. So let's walk through those 6 steps now. So the knowledge capture aspect, this really all pertains to the fact that the information that the computer is capturing is unstructured. So again, for the first time now with AI, instead of storing information in a database, and obviously a database has a hierarchy of highly structured database tables, and then within the tables you have fields. What you're having to do in that example is shoehorn or force fit analog information into that highly structured digital format. Well, that actually is not a very useful or efficient way of storing historical information when it comes to projects or scheduling. Because when you think about it, historical information from a project, sure, it may have a CPM schedule, which is arguably structured information. It may have cost information. Well, that cost breakdown structure may not necessarily match the work breakdown structure in the schedule. There may be multiple documents with regards to change requests or change orders. So that information certainly is not a good candidate to be stored and mined in a structured database. Risks, issues, action items, even things as simple as email dialogue in the project, all of that information is what we call unstructured data. So there is an alternate way of storing this type of information. Some of you may have heard of the phrase NoSQL. We're still storing the information digitally, we're just not storing it in formal tables and fields and so on and so forth. And then the benefit there is that unstructured data in that NoSQL database can be very quickly and efficiently interrogated and mined, and more importantly, patterns found between that unstructured data. So now for the first time, we're able to capture these very large volumes of historical project information, and again, for the first time, actually start to do something with that information. Now, with regards to doing something with that information, before the magic of the AI engine, as we saw in our little neural network example, before that can actually be effective, we have to somewhat train the computer. And the way we train it is, and this is called knowledge classification. What we're doing here is we're trying to decorate that unstructured data with as many attributes as possible. And again, this is all such that the computer then can best understand context when the planner is putting the plan together. So to give you some examples of some of the classification metadata that is useful, often it's beneficial to tag or flag different elements or different projects with geographical location. Another simple example is to classify projects by business unit. The third one's quite interesting, complexity. If you have multiple historical projects and some of those projects were run-of-the-mill projects and some were first of kind, it's probably more likely that your first of kind projects would have experienced more cost and schedule overruns than the run-of-the-mill projects. So by tagging those with regards to complexity, again, the computer's got more information to go against when making its suggestion. So the concept of decorating data with metadata, or we call them tags, really serves 2 purposes. The first is it helps the computer better understand context, which means when it goes off and makes its does its interrogation and makes its selection, it's going to come back with more relevant data. Secondly, though, it also allows us to do what we call knowledge normalization. And this is really, really powerful. So what this allows us to do is through those metadata tags again, let's say, for example, the computer comes back and says, for this particular design element, Dan, the work typically would take 50 days. And let's say I've estimated 30 days, so I've underestimated the duration. Well, if the computer, though, would say, hey, Dan, it takes 50 days, but historically that 50-day estimate was because of first of breed projects or because of a specific location, then that helps the computer normalize and say, well, actually, under normal working conditions or under different geographical locations or under lesser complexity projects, that 50 days actually could be as little as, say, 40 days. So it's a very interesting concept where the computer's not just coming back with a single number or a single answer, it's coming back with an answer and giving me context and also saying, well, based on the conditions on the type of project that you're working on, that 50-day duration actually could be arguably less. So again, it's giving me more background information, it's giving me more hooks against which I can make an informed decision as to whether I go with my 30 days, my 40 days, or my 50 days. So the third step in machine learning is, as I mentioned, knowledge weighting. And again, in very simple terms, this is simply saying each of those attributes, if it carries a weighting, then as the computer makes its suggestion, if the planner or scheduler either adopts or rejects the computer's suggestions, then the computer should be able to learn what is primarily from the rejections and say, okay, I'm giving too much emphasis to certain attributes. I'm coming back with these suggestions. These suggestions are not correct. Therefore, I'm going to adjust the weighting and importance of those attributes until the point at which the planner and scheduler and the end users of the software are starting to adopt more of the computer suggestions. So this is the machine learning aspect of AI and planning. And again, I think this is incredibly powerful because really what it means is, the more the software is used, the smarter it will get and the more accurate its suggestions will get over time. And this is something that from a software perspective, we've never been able to do prior to the advent of AI. All right, so 3 more steps. So now we're rolling into the role of the planner. So again, to perhaps provoke somewhat, I am suggesting that CPM scheduling does not fit all phases of a project lifecycle. In fact, I'm going to be bold enough to say that during the early concept, pre-concept, pre-sanction phase of a project, I would argue that CPM scheduling and the complexity involved around putting that CPM schedule together with calendars and logic links and constraints and all the stuff you have to use to build a CPM schedule, I think it's the wrong tool. I think instead we should be looking at building a top-down timeline. Surely it would be better to start off with the high-level quantities, perhaps from our high-level estimate, and use those quantities to establish high-level timelines. And those timelines then can have associated deliverables. Again, remember in the introduction, I said, we really need to start linking scope of work to the work itself. Well, let's start with the scope of work. Let's define those deliverables. And against those deliverables, if we have a high level of understanding with regards to quantities of those deliverables, it should be fairly straightforward to apply some form of productivity rate to those quantities to establish those high-level timelines. And I call those timelines planning packages. And again, I think it's really important to note here, these planning packages, they don't fall into the complexity of CPM scheduling. All we're trying to do at this point is get a high-level timeline. That timeline can also carry costs, which will give us a high-level cash flow for the project. This is a much more effective way of building an early phase top-down schedule rather than forcing ourselves into the complexity of a CPM schedule. And again, with regards to artificial intelligence, because we have this historical information stored in the knowledge library, it's very straightforward for the AI engine to come back with suggestions and say, historically, these were the top-down timelines, and the computer can make those suggestions and say, okay, well, here's your timeline listing. Not only is the listing made available, The durations for those listings can also be pulled from historical information, as can cost as well. So then we get this three-dimensional, we get the breadth of scope, we get the depth of duration, and we get the depth of cost as well. So this is a much more effective way of putting together an early phase time estimate. So after saying that CPM scheduling is perhaps not the best tool for early phase planning and scheduling, I still do believe that CPM scheduling has its place when we get into detailed planning, detailed design phase within a project. What I do believe is that we need to augment the traditional CPM approach, as I've previously described. You know, again, if the computer can guide me as the planner and come back and say, okay, Dan, well, not only, you know, these are the durations that you should be looking at, but imagine if the computer could even come back and suggest relevant sequence. You know, Dan, these procurement items are going to be delivered too late relative to early phase construction. Well, that would be absolutely incredible. For the first time, you know, I wouldn't have to mentally do the maths and say, okay, well, I need so much lag or buffer between my procurement delivery and my installation campaign, for example. If the computer can look back on historical projects and understand that sequence and that overlap, then that becomes very, very powerful when I'm putting my plan together. At sort of a more fundamental level, again, the AI engine should be able to also make suggestions as to, I call it chunks of scope, but in the technical phrase is subnets. You know, if I'm defining I've got my timelines in my early phase schedule. If I'm a less experienced planner, then, you know, I have the challenge of going off and understanding what are the very detailed activities and the sequence of work in those activities. Well, again, if the AI inference engine can make suggestions as to what those subnets should be, then that takes me down the path of really intelligent templating. And then again, to add to that, wouldn't it be incredible if those subnets that I've embedded into my schedule, wouldn't it be amazing if the computer knew how to tie those subnets together? Well, because the AI engine understands logic, it can look backwards and it can look forwards across activity sequences and come back and say, okay, Dan, you've missed certain logic links here. You know, this is going to have a detrimental impact on the overall timeline of your project. And then in addition to that, the last bullet point on this slide pertains to risks. So the value here is really in a traditional planning environment. You know, many projects will put together a plan or a forecast, and they will then hold what's called a risk workshop, where, you know, the project team have a brainstorming session on potential detrimental risks and their associated impacts. And those brainstorming sessions can often be, first of all, very time-consuming and somewhat tedious. But again, you're also relying on the experience and expertise of the team members to come up with non-biased insight into those risks. It's natural for team members to want the best for the project and not necessarily think objectively as to the potentially bad things that could happen. Well, if we have a historical track record of prior projects, and again, if we can store those risks that actually occurred on previous projects, then through that inference and that context understanding and the pattern matching, the computer should be able to come back and actually decorate our schedule with common risks that happened historically. Now, of course, you know, why is that useful? You could argue that it's actually just making our forecast worse. It's not making our forecast worse. It's making it more realistic. It's highlighting hotspots in our schedule that are going to trip us up in execution. If we understand those hotspots early on, then we have a fighting chance of upfront mitigation and risk reduction, so that they actually don't occur. So it's increasing the confidence and realism in our plan at a very, very early stage. So then we get on to step 3, and again, I think this is really, this is definitely a cutting edge concept with regards to project planning. So historically, by the time we get to project execution, the planning is typically, or has typically been carried out using whiteboards or post-it notes or I hate to say it, but you know, even using Excel. And I think in many ways the reason why those basic tools have stuck is there isn't the need in the field for very complex long-term look-aheads. We're literally doing a you know, 1, 2, 3 week short-term plan, and we've already got the very big picture planned as defined in our CPM schedule. What we haven't got though is the daily, for example, crew allocation. Okay, I'm a foreman responsible for a certain number of crews, and it's my responsibility to assign work to those crews in an optimal manner, taking into account not just sequence of work that came from the CPM schedule, but things like physical constraints, vertical constraints on site, are the materials available in the laydown yard, so on and so forth. And so that very short-term planning exercise relies massively on you know, the foreman's experience and understanding of the job site. Well, again, because we're now moving into this world of non-structured data, and the computer can start to understand all of those variables, you know, things like job constraints, availability of materials, so on and so forth. Because of that, the computer now can also act as a digital planning platform for field execution. So, you know, we've termed this short interval planning, and the concept here is that, you know, you still start with your CPM schedule. That gives you your big picture, your weekly, your monthly timelines, all tied back into the big picture project. But then against those individual CPM activities, that's where the computer can actually assist with defining the daily steps in our short interval plan. And I think, again, a really interesting area that we're certainly working on right now, and I think it's going to have a massive difference in the efficiency in field execution, planning and execution, is tying things like productivity rates back to the work. So what I mean by that is, for the first time, if the computer understands the demand that the work is asking for, in other words, okay, this particular activity, we're doing a concrete pour, and the concrete pour involves so many cubic yards of concrete. Okay, well, if the computer knows the demand from the work, and it also understands how many people in the crew and historical productivity rates, in other words, historically, how fast can those crews work, it can marry up those three variables together and come back with an accurate forecast in terms of how many days it'll take to establish that work. Not only that, if in the short interval planning, this field execution planning exercise, if the computer can also be used as a capture mechanism for, okay, well, here's our plan for the next 2 weeks, but in reality, you know, we had a delay, you know, on a certain day due to unforeseen weather conditions, or the rebar wasn't available as expected. The actual productivity can be captured, and then those productivity rates, of course, if we feed them back into the knowledge library, the next time around when the computer's making suggestions as to how long in the sequence of those steps, it can take into account that updated productivity rate. So it's this self-improving knowledge enrichment cycle that I think from a field execution perspective is very, very exciting. So what I've shown you there is really a 3-step process to project planning. And again, I can't emphasize enough, you know, that's somewhat of a step away from just saying, hey, we're going to use a CPM scheduling tool for planning. You know, we started off with our pre-planning, our top-down estimating. And again, I think the key here is the fact that we're not just arbitrarily coming up with durations or timelines. Everything starts with quantities and scope. It goes back to my comment earlier about really, you know, let's start thinking in terms of deliverable-based planning, not just work-based planning. Imagine if we could do takeoffs from, say, 3D models, 2D drawings, and do quantity takeoffs, use those quantities as the starting point for defining those top-down timelines. When we then get into more detailed planning and the design phase, we don't then start with a blank sheet of paper when building our CPM schedule. Use that high-level planning package-based schedule, which of course was derived from quantities, the first step. Let's use that as a starting point to then build out a more detailed CPM schedule. And again, let's use the experience from prior projects and let's let the computer augment and guide us through what those durations, those costs, and the sequence of work should be. And then as I just showed on the previous slide, when we get into field execution, again, let's not start with a blank sheet of paper. Let's use that CPM schedule that's been validated by the computer, and let's use that as a framework against which to build our daily work plan out in the field. So, you know, what I'm kind of standing on my I guess soapbox here and shouting from the rooftops about is the fact that, you know, let's not replan starting from scratch in each of those three phases. Let's have this continuous flow of knowledge all the way from early concept through planning, through execution, all the way through closeout, and then let's close the loop. That closeout information obviously has our actuals, our actual performance. Let's capture that actual performance, store it in the knowledge library so that the AI engine can then use it to the benefit of the next project. So we've walked through you know, the multiple stages of a project, and I think, you know, maybe one of the take-home points from this webinar is actually illustrated on the screen here. So prior to AI being embedded into planning software, you know, really computers were dealing with the first two elements on the screen, the data and the information. So data, you know, things like, it could just be a simple element such as an actual cost or a risk event or a quantity. That data has historically been stored in a database. Pretty straightforward, pretty standard stuff. Planning tools and scheduling tools and estimating tools and value analysis, risk analysis, those tools really take that data and convert it into information. And that information is really, it's more of an observation. It's saying, okay, I'm going to take the actual cost and the planned cost data elements from a database. I'm going to compare the two and come up with an index, and that gives me an indication as to, you know, an index with regards to performance. Okay, that's great, but prior to AI, the intelligence factor, okay, well, should I be concerned about that CPI or that SPI? That intelligence factor still fell on the shoulders of the human. Well, that's where AI is turning this on its head, because now for the first time, the computer is actually having understanding and saying, well, okay, I get that the CPI is X or the SPI is Y. Yes, you should be concerned about that, or no, you shouldn't be concerned. Again, based on the pattern that it's understanding or seeing from historical projects. So this concept of intelligence now being partly undertaken and partly owned by the computer, I think is a really fascinating. It's a fascinating evolution, and I think, you know, if I as the planner get to focus on, you know, the important things and have to worry less about mundane going off and pulling historical information and things like that, then that benefits me. So I don't feel threatened in any way that, you know, AI is taking over my role or my job or my expertise. It's the opposite. It's actually augmenting and helping me. So before we wrap up, I'd like to talk a little bit about really a convergence topic. So again, you know, in the last 20 years, the science of CPM scheduling it's evolved at a fairly natural pace. And I think probably about 10 years ago, a sibling science emerged or became somewhat mainstream in the form of risk analysis or risk management. And really the benefit and the concept here was the fact that you could take a CPM schedule or a cost estimate, and you could run what we call a Monte Carlo simulation, a risk analysis, and it would come back with a risk-adjusted forecast. And for those of you that have conducted such an analysis, you'll know that the difference between the risk-adjusted view of the project and the deterministic, the CPM version of the project, the difference between the two is contingency. And so that contingency then, it has always been somewhat of a reactive measure. It's been a bit of a cover ourselves measure. Okay, the schedule says 24 months, the risk analysis says 28 months. Let's just add 4 months to the project. Well, that's a very kind of passive, reactive approach to planning and forecasting. Where I believe we should be headed as an industry is to say, okay, as we're putting our plan together, surely if we understand the risk events and if we understand the uncertainty pertaining to durations, and in my experience, durations in a project are primarily, or the uncertainty of duration is primarily driven through quantity growth. Again, because we're overly aggressive, optimistic in our early planning, specifically in the design phase. If, when we're building our plan, the computer can give us insight into the risk-adjusted version of that plan as we build the plan, then there is no concept of going off and doing a risk analysis. As we're building our plan, we are inherently building a risk-adjusted view, and I believe that risk-adjusted view it's a much more realistic version of the truth. A regular CPM schedule, it's not the most likely scenario by any means. It's the best case scenario. Well, why on earth would we kid ourselves that the best case scenario is going to happen in our project? Yes, I believe we all like to be optimistic and want the best for our project, but we also have to be realistic in that forecast. And so if we can account for those uncertainties, that scope creep, those quantity growth areas, those negative risk events, and actually incorporate them in the schedule up front. If we don't like the answer, then we can start to do things like schedule acceleration and compression, rather than just doing the risk analysis after we've put our plan together, after we've agreed on those timelines. So, I truly believe that the science of CPM scheduling it's really getting, I guess, 2 kicks in the butt. I would say, one, that this concept of AI and leveraging historical information. It's whether you believe it today or not, it's going to turn scheduling on its head. Gone are the days where we just arbitrarily define durations and sequence. Again, CPM scheduling, it's the science of forecasting the future. And if we can use historical experience to better forecast the future, that has to be a good thing. And then secondly, again, this concept of let's start thinking, when building our plan, let's start thinking in terms of a risk-adjusted forecast. Let's look at the potential upside and bad side and incorporate that into our plan. That way, as we move forward, we are marching to a most likely scenario rather than a best case scenario. So a few takeaways, and then I think we've got a couple of minutes for the Q&A. In terms of observations, I can't emphasize enough that AI and machine learning is without question turning the interaction between a computer and a human absolutely on its head. For the first time now, the computer is actually talking back to me and giving me suggestions, and then through my acceptance or rejection of those suggestions, the computer is getting smarter and learning. And so I think the industry now is finally turning towards becoming more of a knowledge-driven community, and the science of planning and scheduling is now knowledge-driven rather than the traditional silo-based approach to planning. Now, as with all things in life, or all good things in life, comes some bad and some challenges. I think the biggest challenges today with regards to AI, first of all, you have to have sufficient data capture. You have to have historical information against which to mine. You also have to train the computer, and we talked about the classification, the adding of metadata. That is not it's not a minor undertaking. This concept of bias, if you think about the fact that if the objective of the AI suggestions is to try and reduce human bias, then we also have to just be concerned or just take into account the fact that the computer itself can also carry some degree of bias based on that historical information. And so normalizing that historical knowledge is certainly an area that we're still working on at InEight, and I know other organizations are taking very seriously as well. I think the benefits are self-explanatory. Again, anything we can do to eliminate this terrible concept of silo planning, anything we can do to help validate and calibrate the plans we're putting together has to be better than what we have today. Looking forward to the future, we are definitely, we're running very fast as an industry with regards to AI and machine learning, but we are in the, we're in the early part of our journey. I think over time, and this will be a matter of months, not years, and certainly not decades, the smartness, the cleverness of these inference engines is just going to increase absolutely tremendously. And I think, if the machine learning, and it will, if the machine learning can get smarter, then as soon as we start to get more confidence in the suggestions that are being made, I think the floodgates are going to open. So really, all of this, we've talked about AI and machine learning and risk-adjusted scheduling. The underpinnings of all of that actually rely on the fact that we're undergoing this transformation as an industry today with regards to digitization of knowledge and information. We're finally moving away from analog and disparate information. The digitization of information is pretty straightforward. You can scan a PDF, you can capture a historical schedule. But again, it's the concept now that information can be very comfortably stored in a non or unstructured manner, and more importantly, then computers today are able to mine through that unstructured information and come back with intelligent matches. So that was what I wanted to share with you all today. I think we may have some questions.
Thanks, Dan. Yes, this is a great session, and we do have quite a few questions. So I'll just start right away. So this seems like a breakthrough in planning. So to make sure that AI works properly, obviously historical data is an important foundation. Is there a standard to choose a specific project for the historical data?
Gosh, so the simple answer is no. And the reason why the answer is no is I'm not sure there even is a standard project. Every project by definition is a unique endeavor. Really the concept here is more pattern matching. And again, one thing I didn't mention in the webinar is the fact that when the computer comes back with a suggestion, it's actually not coming back with a single suggestion. It's coming back with multiple suggestions, and each of those suggestions carry a confidence level. And that is a confidence level that the computer believes it's got the right answer. This concept of AI is not a binary science. And so I think it's okay. I think it's actually more valuable that the computer comes back with suggestions from multiple historical projects rather than just saying, hey, based on the purest historical best case schedule, the answer is X. So it's okay for the knowledge library to store a variety of project types. I think it's equally okay for the knowledge library to store projects that went very badly, as well as projects that went very well. In some ways, if the computer says to me, hey, Dan, this is a project that went badly, that's as useful to me as, hey, this is where you should be aiming for to achieve the best case scenario.
So it isn't necessarily about the format of the data, it simply is about the data.
It is, in fact, the format is, we've got the AI smartness to the point where the format of the data is almost irrelevant, and that's where those multiple attributes come into play.
So one of the questions that often causes us to struggle is who's responsible for teaching the computer to get smarter?
So the teaching area, I'm smiling at this question because this is one of my favorite topics because it's really exciting from a software perspective. So there's a couple of approaches we could have taken with regards to training the computer. One would be a traditional approach where you physically have to sit in front of the computer and train it. You tell it good dog, bad dog, right? Well, when we sat down and just thought about the design and the approach that we've taken, that's actually quite tedious and quite inefficient, because during my 8 hours of working every day, I've probably got better things to do as a planner than sit down and train a computer. So what we said was, well, if the computer is interacting with the human, me the planner, wouldn't it be amazing if the computer could pick up on that interaction? And that's exactly how it works. So as the planner is presented with suggestions, the planner then either adopts those suggestions or partially adopts or rejects or somewhere in between. Well, the computer then understands those acceptances and those rejections, and it's that behavior of the planner that it uses to do its learning and its machine learning. Does that make sense?
So does this happen inside of the organization's CPM or work-based planning or scheduling softwares like P6?
So this doesn't actually take place in the likes of P6 itself. What we've done at InEight is developed this AI planning assistant that sits alongside P6. So all of the smarts with regards to knowledge capture, the classification, the dishing up of suggestions, and then to answer your question, the machine learning on the way back, all of that is absolutely within the InEight planning assistant solution.
I see. So it's kind of works hand in hand.
It's hand in hand, and again, the reason for that is, just from a practical perspective, we recognize that many organizations have already invested in their scheduling tool of choice. For me, and certainly at InEight, it's not very exciting or interesting to change that behavior for the same thing. What we're doing is adding benefit to it. And so, yes, our AI engine and the machine learning, all of that sits alongside your planning, scheduling, estimating tool.
So changing gears just a little bit, to what extent does the system respond to new scenarios that may not have a historical basis?
Okay, so if the system, let's say I'm working on a completely new type of project and the computer can't mine analogous historical information, perhaps this is, this project type's never been done before. There is a safety net mechanism built in there where the computer says, okay, look, I'm not able to give you sufficient information. What I'd like to do is go off and canvass other team members on the project. So what happens there is the computer invites other experts on the project to give their expert opinion. Those multiple expert opinions, we call this process a markup process. And I like to call this human intelligence. It's the blend of the computer dishing up the AI and then the team members dishing up the HI, the human intelligence. Those team member contributors all give their expert opinion, and then those opinions automatically then end up in the knowledge library. And again, it's all feeding back into the AI engine. So even if the computer doesn't have historical information, it's smart enough, and again, it's humble enough to stick up its hand and go, okay, I can't give you a meaningful answer, but what I'm going to do is go and get the information from domain experts, discipline leads. And so it's actually a really, really clever way of feeding and populating the knowledge library, and backfilling those white space knowledge areas within the library.
Awesome. So how does a trained machine generalize its capabilities for prediction specific to a variety of types of construction projects? And does that just all double back to the data necessity and the crunching, or is there a more specific methodology that you could explain in the next minute?
Okay, so I think if I understand your question correctly, you mentioned the concept of generalizing. So in the world of pattern matching and computing, there is this constant battle between generalizing but also being specific enough that you come back with something useful. So
right.
Again, for example, when you start off at that top level, high level, top-down planning, the computer will actually ask you, okay, well, what is the type of project, the location, do you know the subcontractors? And it's asking for these points of context. So it uses those points of context such that it can then go off and come back and cast the net against relevant historical information. And then at a more detailed level, so that gets it specific enough, but then at the very detailed activity level, you actually want the inverse to happen, because then you want to be somewhat general, because if I'm typing design and analogous scope in the knowledge library is called ENG or engineering, then that's at the point where you need to be general in your matching. So it's sort of this inverse relationship between, at the very high level, you want the computer to be specific, but at the very detailed activity level, you want it to actually generalize on things like descriptions. And again, that's all built into the AI inference engine. It actually adjusts its generalization of search or specificness of search depending on the level of detail that you're at.
Thank you so much, Dan. This was very informative about what AI could do and possibly will be doing shortly to deliver projects and predictive planning. I want to thank you and InEight for putting together this amazing webinar. And for those people who submitted a question and we were unable to get to that question, we will send you direct messages just answering that. And the presentation will be made available on the CII website later this month, but all of the registrants, whether you attended or were unfortunately unable to attend, will receive a recording. So what a wonderful presentation, and thank you so much, everyone, for attending, and stay tuned for future CII webinars. Again, round of applause for Dan and InEight.